Hello, I am Dr. Imran Khan. Today we are going to discuss embedded system technologies. An embedded system is a combination of computer hardware and software designed for a specific function or function within a large system. The system can be programmable or with fixed functionality. Industrial machines, consumer electronics, agriculture and process industry devices, automobiles, medical equipment, cameras, as well as mobile devices, all are the possible locations for an embedded system. So before going to the embedded system technologies, we should define what is an embedded system. An embedded system is a combination of hardware and software which together forms a component of a larger machine. An example of an embedded system is a microprocessor that controls an automobile engine. An embedded system is designed to run on its own without human intervention and may be required to respond to events in real time. So this is the possible schematic of an embedded system. So here you can see that the central processing unit or CPU is connected to many input output devices. So here you can see these are the input devices and these are the output devices and the sensors. So these sensors are used to measure physical values and the actuators on the output. So actuators are used to control physical things. So also you can see the CPU is connected to the permanent memory for storing the data. So these all connections are made by using system buses. So system buses are used for communication uh, inside an embedded system. So the system bus has three types: address bus, data bus, and control bus. So this is the possible schematic of an embedded system. So to be good in embedded system, you should need to know about digital logic, electric circuits, and computer architecture. So these are uh, the basic courses which you are required before taking an embedded system course. So the embedded systems are everywhere. So you will find embedded system in medical, in automotive industry, in military applications, industrial applications, consumer electronics, mobile phones, everywhere. So these embedded systems are invisible. These are hidden. So these are the computers inside the devices, and they are dedicated purpose devices. So the possible microprocessors which you can use as an embedded in the embedded systems are maybe the Intel microprocessors. So they developed a lot of good microprocessors. So and they are developing from 1970s. So you can also use the Freescale microprocessors, ARM microprocessors, and there are also some microcontrollers. So the microcontrollers, they have processor, memory, IO devices, interfaces, everything on a single chip. This is the possible circuit of an embedded system. So here you can see the microcontroller IO ports, and these IO ports are connected to many other electrical, mechanical, chemical, or optical devices. So here you can also see ADC, analog to digital converter, and digital to analog converter, and the buses are used for the interface. So now we should start with the main topic of our today's lecture. So today we will discuss the three key embedded system technologies. So what is technology? Basically, a technology is a manner of accomplishing a task, especially using technical processes, methods, or knowledge. So there are three embedded system technologies which are extensively used in the embedded system. So number one is the processor technology. number 2 is the IC technology, and number 3 is the design technology. So we should describe the microprocessor technology first. A microprocessor is an integrated circuit which incorporates core functions of a computer's central processing unit or CPU. It is a programmable, multi-purpose silicon chip, clock-driven, register-based that accepts binary data as input and provides output after processing it as per the instructions stored in the memory. So the microprocessor is similar to our human brain. It can be trained to do anything. It can be programmed to do anything we want based on its instruction set and capabilities. Sometimes solutions are very complex. Circuits also becomes very complex if you try to solve it without programming. So a processor is the brain of computer, which basically consists of arithmetic and logic unit, control unit, and register array. As the name indicates, ALU perform the arithmetic and logic operation on data received from input devices or memory. Register array consists of series of register like accumulator, register A, B, C, D, etc., which acts as a temporary fast access memory location for processing data. As the name indicates, control units controls the flow of instruction and data throughout the system. So we have three basic types of the microprocessors. So if you see the figure here, so we have the three processors here. So these three different types of microprocessors are separated uh, with this dotted line. Okay, so the first one is the general purpose processor. The second one is the application specific microprocessor, and this third one is the single purpose processor. So here you can see the controller and the program memory, these data paths, register files, so the general ALU, data memory, and you will find the similar things in the application specific microprocessor, but the difference is in ALU. So in the general purpose microprocessor, the ALU is general ALU, but in the application specific microprocessor, it's custom ALU. So in the single purpose processor, so you will find the controller, data path, and some data memory. Okay, so let's describe these processors in detail. Okay, so the general purpose processor. So these processors are programmable devices used in variety of applications. So these are also known as microprocessors. So some good features of these general purpose processors are that they have some program memory, general data path with larger register files, and general ALU. So these general purpose microprocessors have some user benefits, like they have low time to market and low NRE cost. They have high flexibility. So a good example of general purpose processor is the Pentium computer. So here you can see the block level diagram of this microprocessor. Okay, so here you will find the controller, program memory, data path, and the register files, general ALU, and the data memory. So the single purpose processors are the digital circuit designed to execute exactly one program. So these are also known as coprocessor, accelerator, or peripherals. So the features of these single purpose processors are they contain only components needed to execute a single program. So they don't have the program memory, they are fast, they have low power dissipation and smaller in size. So here you can see the block level diagram of single purpose microprocessors. So the application specific microprocessors. So the application microprocessors are programmable processors optimized for a particular class of applications having common characteristics. So the good features of these application specific microprocessors are they have some program memory, they have optimized data path, and they have special functional units. So the benefits include they have some flexibility, good performance, size, and the power dissipation benefits. So here is the block level diagram of this application microprocessor. So here you will find the custom ALU or custom arithmetic logic unit. So these microprocessors we already described in our previous lecture in detail. So if you want to know the detail, you can see the previous lectures. So the IC technology. In earlier days, embedded system devices were designed using vacuum tubes, would be very large in size and more expensive. The first point contact transistor was developed by John Bardeen and Walter Brattain at Bell Labs in 1947. Then the invention of transistor has reduced and replaced the bulky expensive vacuum tubes in computer design. Subsequently, the transistor usage reduced the size of circuit as these transistors are less in size, economical, faster in performance, reliable, and consumes very less power. So circuits built using transistors and other discrete components are called discrete circuits. Revolutionary change was made in designing electrical and electronic circuits and computer with the invention of an integrated circuit or IC technology. Integrated circuits are very complex and very small in size. They are very reliable, most economical, and very simple to use. This concept of IC design was introduced in 1958. And this IC technology miniaturized a lot of electrical and electronic components like mobile phones, laptops, computer, and many other devices. So integrated circuit can be defined as a set of electronic circuit integrated on a small semiconductor material plate, typically called a silicon chip. Each IC can be very compact, containing billions of transistors and other components on very small area. So here the basic building block of our IC technology is the transistor. So here you can see the transistor. So here this is the gate, source, drain. So the transistor basically you apply voltage at the gate terminal and control the current between the drain and source terminal. So if you want to know more about the working principle of the transistor, please see our previous lecture. So there are three types of IC technology: full custom or VLSI, semi-custom, ASIC or gate array, and standard cell IC, PLD, or programmable logic devices. So the full custom design is a methodology for designing integrated circuit by specifying the layout of each individual transistor and interconnection between them. So in full custom or VLSI design, all layers are optimized for an embedded system's particular uh, digital implementation, like placing transistors, sizing transistor, routing wires. So there are some benefits of full custom design. They have excellent performance, they are smaller in size, and they have low power dissipation. So similarly, they have some drawbacks like high NRE cost or non-recurrent engineering cost. So this is the first time design cost. So it is around 300,000 US dollars, and they have long time to market. So the semiconductor designs, semi-custom IC designs. Semi-custom IC design is a methodology for making an integrated circuit in which a portion of circuit function is predefined and unalterable, while other portion can be configured to meet designers' specific needs. So the designers have the capability of designing application-specific circuits themselves using either standard cell libraries or pre-configured arrays. In semi-custom ICs, all the logic cells are pre-defined, and some of the mask layers are customized. Using predefined cells from cell library makes our lives as designers much easier and faster. Therefore, semiconductor ICs are less expensive to manufacture and designs. So the semi-custom ICs have some benefits, like they have good performance, they are smaller in size, they have less NRE or non-recurrent engineering cost. If we compare with the full custom implementation, so they have the NRE cost from 10,000 US dollars to 100,000 US dollars. So they have some drawbacks, like they still require weeks to months to develop. Programmable logic devices. So in programmable logic devices, all layers already exist. Designers can purchase an IC connection on the IC, are either created or destroyed to implement desired functionality. Here you can make your own connection, and you can also remove the previous connections. So field programmable gate arrays, FPGAs, are very popular in these kind of devices. They have some benefits, like they have low NRE cost, and they also have some drawbacks, like they are bigger, expensive, and they have more power dissipation. Basically, they are power hungry, and they are slower. Moore's law. Uh, the most important trend in embedded system design was predicted by Gordon Moore. So he predicted in 1965 that uh, the IC transistor capacity has doubled roughly every 18 months for the past several basically, he predicted that the semiconductor industry will uh, double its effectiveness after every 18 to 24 months. So this Moore's law has driven the semiconductor industry for many decades. So here you can see the trend between the number of years and the number of transistors. So number of transistors on an integrated circuits are continually increasing. So nowadays we have billions of transistors on small silicon area. So design technology. So design technology is a procedure for designing a system. Many systems are complex and pose many design challenges: large specifications, short time to market, high performance, multiple designers, interface to manufacturing, and many other things. So proper design methodologies help to manage the design process and improve the quality. A sequence of design steps in design methodology is software engineering tools, compilers, computer aided design tools, etc. So the design technology is the manner in which we convert our concept of desired system functionality into an implementation. So here you can see the system level specifications, behavioral specifications, RT specifications, and uh, logic specifications to the final design. Okay, so here you will see uh, the compilation process or the synthesis process. So it basically automates exploration and insertion of implementation detail for lower level. So this behavioral specifications uh, basically they incorporates pre-defined implementation from lower abstraction level to the higher abstraction levels. So in the RT specifications and uh, logic specifications, so it's the test verification process. It basically ensures correct functionality at each level. So here you can see the compilation synthesis uh, and the libraries and test verifications. So this is the possible block level diagram of design technology, which is extensively used in our embedded systems. Here you can see that the design productivity is increasing exponentially. So here you can see the trend. So these are the number of years, and this is the productivity transistor per stop. So you can see that there is a exponential increase in the productivity over several past few decades. Okay, so here you can see there is an exponential increase. So the design productivity gap in 1981, leading edge chip required 100 designers per month. In year 2002, leading edge chip requires 30,000 designers per month. So, so there is a gap between the design productivity and the designers. Okay, so here you can see the diagram, the 3D diagram, um, and it's a basically relationship between the number of transistors, number of years, and the productivity. So here you can see the productivity and the IC capacity. So still IC capacity is much more compared to the productivity. So still there is a gap. It means that still we need more good and trained people in the integrated circuit design or the embedded system technologies. So this was all for today. So if you have any question, please feel free to contact me via email. So thank you very much for today. See you next time.